Hi everyone, I'm Cheryl. In this example, we're looking for the degree of the Maclaurin polynomial that will allow me to approximate f of x equals e to the x when x is 0.6 with an error that's less than 0.001. Now we're going to make use of something called Taylor's theorem. Taylor's theorem allows me to get a Taylor polynomial, and it also talks about the error involved in finding that Taylor polynomial. But I'm going to be using a consequence of that theorem. My consequence is that the absolute value of the remainder is less than the absolute value of x minus c to the n plus first power all over n plus 1 factorial times the maximum of the n plus first derivative at z, where z is somewhere between c and x. Now, what does this mean for our particular problem? Well, first of all, we're looking for a Maclaurin polynomial. A Maclaurin polynomial is just a Taylor polynomial that is centered at 0. So in this problem, the c values will all be 0. So let's take a look at what else I can fill in. I know that I'm looking for the remainder when I'm near 0.6. So I'll plug 0.6 in here, and that's going to be less than, this will be the absolute value of 0.6 minus 0, again, because it's centered at 0, to the n plus first power all over n plus 1 factorial times the maximum of the absolute value of the n plus first derivative. Now remember, what is my function? My function is e to the x. The derivative of e to the x is e to the x, whose derivative is e to the x, and the third derivative is e to the x, and so on. So the n plus first derivative is going to be e to the x. Evaluated at z is going to be e to the z power. And I'm going to evaluate this when z is between my center at 0 and x, which is 0.6. Okay, now let's see what this gives me. I now have 0.6 minus 0, which is 0.6, and that's a positive number, so I don't need the absolute values. So that's just 0.6 raised to the n plus first power all over n plus 1 factorial. Now let's take a look at this next part, the maximum of the e to the z, and z is somewhere between 0 and 0.6. Remember what an exponential function looks like. An exponential function is always increasing, which means that between 0 and 0.6, it's going to take its largest value on at 0.6. So this term right here will be e to the 0.6. Okay, so now that I know that my remainder is less than this, and I want this to be less than 0.001. So now I need to figure out a value of n that will make this happen. All right, I'm going to have to do this just by trial and error. So let's go ahead and make a little table. My input values are going to be n, and my output values are going to be this expression. So 0.6 raised to the n plus first power all over n plus 1 factorial times e to the 0.6. All right, so let's try some values. Let's begin by letting n equal 1. If n equals 1, I'm going to have 0.6 squared all over 2 factorial times e to the 0.6. All right, I'm going to use my calculator to help me evaluate that. So 0.6 squared divided by 2 factorial times e to the 0.6 is going to be approximately 0.328. Now remember, I want that error to be less than 0.001. That's nowhere near 0.001. So I'm going to try another value of n. Because I'm so far away, I'm going to skip through a few values. Let's see what happens when n equals 4. When n equals 4, I will have 0.6 to the 4 plus 1, or the fifth power, divided by 5 factorial times e to the 0.6. And if I calculate that, so 0.6 raised to the 5th power divided by 5 factorial times e to the 0.6, I'm going to get approximately 0.0011. All right, now remember, I need this to be less than 0.001. That's very close, but this number is still bigger. So let me try one more time. Let's let n equal 5. So I'll have 0.6 raised to the n plus 1, so that's the 6th power, divided by 6 factorial times e to the 0.6. And again, if I plug that into my calculator, 0.6 raised to the 6th power divided by 6 factorial times e to the 0.6 power, I'm going to get approximately 0.000118. Notice this number is less than 0.001, which means I need a Maclaurin polynomial whose degree is 5. I hope that was helpful. Thanks.